Hello and welcome to another paper. So this time out we're looking at Winter 23, paper 42. This is another homework question, a homework paper. So let's get right into it. So first question, a student measures the spring constant K of a spring using two different methods. Spring constant K of a spring is a measure of the stiffness of the spring. The larger the spring constant, the more difficult the spring is to stretch. Stuff you know from your theory anyway. Method 1, the student measures the unstretched length of the spring to the nearest 0.1 centimeters. A full-size diagram of the spring is shown in 1.1. Measure the unstretched length L0 of the spring to the nearest 0.1 centimeters. So you just place your scales between these dotted lines and you read off what this length is. So when you measure this turns out to be 5.5 centimeters approximately. Do keep the accuracy in mind, so you need to give it to 0.1 centimeters, right? So this is something you should take into account. The student attaches the spring to a clamp on a stand, suspends a 300 grams mass from it. The arrangement of the apparatus is then shown in 1.2. The student measures the new length L1 of the spring, calculate the extension produced by the mass. So the new length minus the old length, that's extension, so 17.6 minus whatever original length we wrote, which was 5.5. So that turns out to be 12.1 centimeters. Calculate the spring constant K1 of the spring. So again, we have the extension. We just need to plug this into the formula. Just note that this is in cm, whereas the spring constant is asked in Newton per meter. So you'll need to convert this to your SI units. So again, 300 was the mass as well. So 300 grams this was. So the mass there was in grams as well, and we are told nothing to do with this. So let's just use this value. Actually, if you do this, if you convert the mass to kg and then multiply by 9.81 and then divide by the converted unit of centimeters to meters, you'll get the same answer if you do this directly as well. So 300 over 12.1 turns out to be 24.79, or let's say 24.8 Newton per meter to 3SF. It is important to avoid line of sight parallax errors when determining the extension of the spring. Explain what is meant by parallax errors and how to avoid parallax errors. So parallax errors arise due to incorrect viewing positions, when taking a reading. And how do we avoid it? This is also really straightforward, is that you place your eyes, so place, or let's say view perpendicularly to the mark being read. Let's go on to the next part. Method 2, the student pulls the 300 gram mass down by a small distance and releases it so that the mass oscillates up and down. Measures the time t1 taken for 20 oscillations. Reading on the stopwatch is shown here. Record the time in table 1.1 to 1 decimal place. So this is not to 1 decimal place, right? So to 1 decimal place, t1, this time is going to be 13.6 seconds. Part 2, the student measures the time for 20 oscillations once more and records the time t2 in table 1.1. Calculate the mean time t for 20 oscillations and record your answer. So I just need to average these. It's very easy to see. This is going to be 13.7, right in the middle of 13.6 and 13.8. So 13.7 seconds. Mean period of the oscillation is the mean time taken for one oscillation. So this was for 20 oscillations. So 13.7 divided by 20 is 0.685, right? So again, when calculating something from a previous value, make sure that the number of significant figures are the same, right? So 0.685, and then t square, so the square of this is 0.469225, so 0.469, or you can say 0.47. So this is done. Now let's go on to the next part. Use your value of t square from the table to calculate the spring constant K2. Again, this is also really easy because you already have calculated t squared, so 11.8 divided by 0.47. So that is going to be 25.106, 25.1. Explain why the value for the mean period t obtained by measuring 20 oscillations twice is more accurate than the value obtained by measuring one oscillation twice. So we know that this is because the greater number of oscillations reduces the impact, the uncertainty introduced by human reaction time. So it reduces the uncertainty because of human reaction time, right? So the same human reaction time, because now it will be part of a larger time, so it's going to be a smaller fraction that's going to have a lower impact, right? Write this entirely. Don't just say that the human reaction time goes down, because first of all, that statement is wrong. Human reaction time would not go down, but instead, because of having this on a greater number of on larger time, so the impact would go down. Question number 2. Next question. A student investigates the rate of cooling of water at the top and the bottom of a beaker of hot water. So the student measures the room temperature, pours 200 cm³ of hot water into the beaker, lowers the thermometer into the beaker until its bulb is just covered by the hot water as is shown. This is the best way to actually take readings using a thermometer, because it's not touching the glass and it's still immersed in the liquid. So then he waits for approximately 30 seconds, starts a stopwatch and reads the thermometer. So the temperature on the thermometer is shown. Record the temperature reading at time t equals to 0 to the nearest 0.5 degrees centigrade. So this is what, 85, and then this looks like 85.5, right? It's between 85 and 86. So this is 85.5 degree Celsius. Explain why the student waits for 30 seconds before reading the initial temperature of the hot water. So he is basically allowing the thermometer to respond to it, right? So allowing the thermometer to respond, right, for the temperature to actually increase so that the liquid basically moves up the tube. The student waits for 3 minutes and records the new temperature reading in table 2.1. The student then removes the thermometer from the beaker and pours the water away. Repeats the procedure in A, but lowers the thermometer into the beaker so that the bulb is just above but not touching the bottom of the beaker. Again, this is also a good way to do it. Records the initial and final temperatures of the water as is shown. Calculate the average rate of cooling of the hot water at the top of the beaker using this equation. So decrease in temperature of the water. So how much does the temperature drop by? So let's see which values do we have to use. So it's the hot water at the top. So it must be this one, which is of the water which is just below the surface. This must be the hotter one near the top. So 85.5 and 78. This difference is 7.5 divided by the time. So we were doing this after 3 minutes. So divide by 3. So the unit will also be in degrees Celsius per minute, because that's degrees Celsius, this is minute, and this value turns out to be 2.5. Next, use data in 2.1 to calculate the average rate of cooling PB of the hot water at the bottom. So for the bottom we have this these temperatures, right, which are near to the bottom. So 86 and 77 is 9. Again, this happens in a time of 3 minutes. So 9 over 3, this is going to be 3.0. Again, do give this as degrees Celsius per minute again, right? Use your answers in B1 and B2 to suggest why a hot liquid should be stirred before measuring its temperature. So why should it be stirred? You can see that for the water at the bottom, because that's where the heat was given from, the temperature rise was greater, right? So to ensure that temperature spreads out evenly, it should be stirred. So this is to mix the liquid and evenly spread out temperature. Next part, state one way in which the apparatus in this experiment is arranged a way to make it easy to read the thermometer quickly. So you can see that the thermometer was positioned in a certain way, but this is about reading the thermometer accurately. So how do you read it accurately? So you can see the thermometer was clamped, right? So since it's clamped, it's held steady, so reading it is easy, right? So since it is clamped, so clamp holds the thermometer steady. So this makes it easy to read. The experiment is repeated to check the results. Suggest one variable that must be kept constant. So again, this is about the cooling, right? So I can say that the room temperature must be the same. You can also say that the amount of water must be the same. You should do it for the same time, right? And a lot of factors that you can write here. So I'm going to say same room temperature. The student leaves the thermometer in the hot water and waits for 30 minutes before reading the thermometer again. Predict a value of the water in the beaker. So it must have been cooled down to the room temperature. Now we should go up and look if we have room temperatures here. Right, so right at the start we were given the room temperature 22.5. So this is also what it's going to be, because it would gradually have cooled down after such a long time. So 22.5 degrees Celsius is the answer for this part. Question 3. A student investigates how the potential difference across the terminals of a power supply changes as the current I in a circuit changes. So you have the voltage across the power supply, there's the switch, ammeter, insulating tape, again a flying lead, and the crocodile clip to connect it at different distances. The student closes the switch and observes the reading on the voltmeter. The reading is shown here. Record the voltmeter reading. Again, very easy to see. This must be 2.9 volts. The student then connects the crocodile clip to the resistance wire. So when he closes the switch and observes the reading, so this is all of this, right? So then this part of the circuit would basically be operational. So we get the voltage of the power supply. This is what we really found. Again, in ATPs, you really don't need to think about what you're doing, but if you do, then it can serve to help you in certain parts. Because if you are somewhere stuck, then you can always think about the experimental procedure in its theoretical terms, what it wants to do. So what you just found out is the EMF of the power supply. The student then connects the crocodile clip to the resistance wire at a distance D equals 100 cm from X. So 100 cm from X would be here. And then he records the potential difference across the wire as this, records the current, and opens the switch again. Also, if you ever have to write like improvements for experiments related to any sort of electricity, you can always say that between readings you should open the switch again, right? So that unnecessary amount of current does not flow. It does not, for example, cause this resistance wire here to get unnecessarily heated up, and it can also reduce the risk of electrocution. So the reading on the ammeter is now given. So this is from 0 to 0.5. So this must be 0.1, 0.2, 0.3. This is 1 after that. So this is going to be 0.31 amperes. The student closes the switch, repeats the values of D for 80, 60, 40, 20. Students' results are shown. Complete the header of each column and include the value of I from part B. Let's do that first. So this is 0.31. So if I look at current, this was in amperes, right? Right here. So this is in amperes. And the voltage reading was similarly in volts. Distance readings were in centimeters. On the grid provided, plot a graph of V on the y-axis against I on the x-axis using the data in table 3.1. Start both axes from origin 0, 0, draw the best fit straight line. So V versus I, right? Again, let's take a picture of these to go. So these are our values here. Again, always in O levels, you will have to start your graph from 0, 0. V is on the y-axis. Let's label this. So this is on the y-axis, V in volts, and x-axis is current in amperes. Now, first value, again, first we need to figure out the scale. So both of these start from the origin, 0, 0, 0, 0. All right. Also, let's see, make this very fine. All right, so then we are figuring out the scales. So you want for the voltage to go up to 2.5. So how about this? 0.5, 1, 1.5, 2.5. Again, let's see if we can still change the scale to indicate, to capture more of the graph. How about 0.5? So 0.5, 1, 1.5, but then this won't happen, right? Then we won't be able to capture those values. So let's just go with this. This is 0.5. This is 1.0, 1.5, 2.0, and 2.5 here. Now for the time axis, we go up to 0.88. So how about 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7? All right, so this is not going to work out either because you have to go up till 0.88. So let's say 0.2, 0.4, 0.6, 0.8. This is the best we can do. So 0.2, 0.4, 0.6, and 0.8. And then this one, let's also mark the next one, 1.0. So now we need to first locate these points. So 2.3, actually 0.31, comma 2.3 is what I'm looking for. So 0.3, this one would be 0.32. So 0.31 would be in the middle and 2.3, right? So this is 0.31 right here. 2.3 for this, again, let's zoom into here. 2.25, 2.3, 2.35, 2.4, 2.45, 2.5. So 0.31 and 2.3 is what we're looking for. So that's going to be here, right? That's a point here. Next, we have 2.2 and 0.37. So 0.37 would again be in the middle, right? 0.32, 0.34, 0.36, and then this is 0.37, and then goes up till 2.2. So 0.37 and 2.2 is going to be here, right? This is that next point. Then we have 0.45, comma 2. 0.45 would be right in the middle of 0.4 and 0.46, 0.4 and 0.5, right? So 0.5 and 2 is going to be here. What is the next value is 0.6 and 1.7. 0.6, 1.7, so that's going to be here. Let's try to make this a bit neater. Then we have 0.88 and 1.2. 0.88 would be right here, and 1.2. 1.1, 1.2. Right, so these are all my points. Now it seems pretty obvious that this is going to be a line, but still let's confirm. So draw the best fit straight line. Again, let's keep a line here. I need a thinner one than this. See if we can manage. So always make sure that your line goes through the entire graph, because you don't know what the examiner could ask of you in a later part. So kind of like this, evening out the distance left above and below. Right, probably something like this, but again, let's make sure it goes through the entire grid. Alright, so this is drawn. The gradient of your line is numerically equal to the resistance of the power supply. Calculate the gradient of your line. Show clearly on the graph the values you choose and show your working. Alright, so one of these values is obvious, which is this one, right? So after 2.5, this must be 3.0, right? So this is 3.0, so one value is 0, 3.0. This is one value. Let's pick up another value which is far away. Maybe this value right here. Right, so this is 1, so it's this one would be 0.75, right? So 0.8, 0.85, and then it's not really 0.9 quite yet. Let's say 0.88. 1.0, 0.88. So 0, 3.0 and 1, 0.88. So change in y over change in x. So 3 minus 0.88 over 0 minus 1. So 3 minus 0.88. So negative 2.12, but it says numerically equal. So I'll just drop the negative sign. So this is 2.12 volts. Sorry, not volts, ohms. This is the resistance of the power supply. And the EMF, the intercept between Y and your line is the EMF of the power supply, which we just used as 3.0 volts. Now, compare the value of V0 in A with your value of V0 that you obtained from the graph in E2. Now, this is where the theory can help you out. Because you know that you were measuring the EMF of the power supply, that's why we knew that that one was 2.9 volts, right? This one that we found out is 3.0 volts. Now we need to show that whether these are, these are within each other's limits or not. So now if I look at this, again I need to do the 10% calculation. So 10% of 2.9 is 0.29, right? So 10% of 2.9 is 0.29. So if I do 2.9 plus 0.29, So 2.9 plus 0.29, this is 3.19, and finally we can see that this is less than the 3 volts, right? So this 3 volt does lie within that range, so I'll say yes, because within 10%. Another student decides to connect the crocodile clip, so there is only a very small length of the resistance wire included in the circuit. The teacher tells the student not to do this. Suggest one practical reason why values of D less than 20 cm should not be used. Right, so if there is a very small length of resistance wire, this means that the resistance is also very less, so there would be a huge current which is flowing, right? So a huge current is flowing. Now we would usually say that it can cause electrocution, but if you remember here, this was covered with an insulating wire, right, an insulating tape. But anyway, the wire can become too hot and also melt the tape, right? So this is something that can happen. So wire may become too hot. And melt the tape. And let's also write here, because of the large current. It is possible to change the potential difference by using a variable resistor, then using different lengths of wire. Complete the circuit diagram shown in 3.5 to show how the variable resistor is connected. So with the potential, with the variable resistor, I can see that this power supply and this power supply and the variable resistor will be in series. So according to the potential difference rule, if the resistance of this increases, the voltage across here increases, and the voltage across here would decrease, right? So this is how the circuit diagram looks like. Question number 4. A student investigates the average speed of a trolley moving along a horizontal bench. Trolley is placed on a ramp and released from rest. Some of the apparatus used is shown in 4.1. So you have the masses, you have a stand from which this ramp is basically clamped, and down this ramp slides down the trolley, and then it goes off on the bench. The stopping distance of the trolley is the distance moved by the trolley from the bottom of the ramp until it comes to rest. So this distance is what we are measuring. Plan an experiment to investigate how the average speed of the trolley along the bench. So we have to investigate how the average speed of the trolley along the bench varies. How till when it comes to rest, how does that depend on the mass? Average speed of the trolley can be calculated using this equation, stopping distance over time. In your plan, you should explain briefly how to carry out the investigation, stating any other apparatus used, state the key variables to keep constant, draw a table with column headings, and the usual stuff. Now again, if I know that what I have to change, I can already gain half the marks here. So I know that for me to see that how the average speed depends on mass, I can see that I have these sets of masses here which can be placed on the trolley, and then it's going to cause it to go forward, right? That's how I can change the mass. And how would I find the average speed? So I can measure the length of the ramp. So how the average speed of the trolley along, so it's along the bench. So for the bench, I can do this, that again, this says average speed. I know that it would practically slow down, but I can find this distance, I can measure the time, and dividing the two can give me the average speed, right? So here, what am I varying? I'll say that I'll vary the mass and measure the average distance and use that to find the measure the stopping distance and use that to find the average speed. So let's write this down. So vary the mass by placing it on the trolley and record the stopping distance and the time it takes for the trolley to come to rest. And then I'll say use the formula to find out to calculate the average speed. So with this done, what else do I need to talk about? So I've talked about this, and yes, I can talk about how to measure these as well. So I'll say measure the distance using the meter rule. And measure the time using a stopwatch. And then I can also say that repeat for at least 6 different masses, right? So then we have 6 sets of values. This is also something that I get marks for saying. Now talking about the key variables, that what should be constant so that the only effect on the average speed is of the mass and of nothing else. So I can say that the angle of the ramp, right, and the height, but again height and angle are the same thing, and you should always release it from the same position, right? This is what I can say. So always release it from the same position and keep the same angle of the ramp. So keep starting position and the angle of the ramp constant. Alright, this is done. Draw a table with column headings to show how to display the readings. You are not required to enter any readings. So here the readings are slightly more than you have in the normal experiments. So you just need to talk about these a bit. Nothing special otherwise. Again, something that you could say, even though it's not really asked here. For example, if you wanted to make this more accurate, you can say that you drop it many times and you record multiple times, right? This is what you could actually say, but it's not required here. So again, let's start filling this up. Serial number, mass. Do make sure the units are correct here. That's what you have masses, that's what you have marks for, because you don't need to enter values here anyway. So mass in grams, distance, again whatever you feel like, meters or centimeters, and time in seconds, right? Again, the last part always the same, so you know what we say. So plot a graph. Oh, so here I just realized that since we are saying we are investigating average speed, so we should also have a column for average speed here, right? So we'll use these values, the distance time values, to find the average speed. So let's make this here as well. So this is your average speed in meters per second. So plot a graph of average speed against mass to make conclusions. So that's this paper. See you in the next one.